All right. Hi. That's still way too loud. Just a second. Hello? Okay. So my name is Matt Simmons. I'm with Google, formerly with School of Information at U of M. And I'm here to talk to you today about R. And this is really just a very brief introduction to R in general. I'm going to start with talking about some of the resources to learn more about R, in case my presentation doesn't leave you with a complete knowledge of the platform in totality. Not on my goal list, but we'll see. Then I'm going to go into some of the data structures, the capabilities of the language, finish up with a couple of examples, and then take questions. So these are my assumptions for the audience of this tutorial, which are, I'm sure, my assumptions will be violated in many different degrees here, that people are familiar with basic statistical concepts, that they are familiar with programming concepts, but they don't know anything about R. So I'm sort of planning on starting from scratch. So what is R? Well, it's a very nice letter of the alphabet, but it is also a free statistical computing package that has its own language that you can write functions in and do all kinds of good stuff. It's free. It's also flexible. Being an open source program, it enjoys the benefits of lots and lots of people that tinker and write their own packages. So if you need to do some sort of standard statistical analysis, there's probably 3 or 4 outdated packages and maybe 1 or 2 current packages in R that will do what you want. It has its own programming language, like I said, which has flow control structures, functions, classes. So actually, it's got 2 class systems, but I'm not going to cover that today. What isn't R? Well, it's not going to give you a really pretty user interface by default. There is a little bit of a learning curve, generally, with R. Some of the GUI applications, which I'll cover in the next slide, help ease that learning curve a little bit. But it's really something that you have to invest a little bit of effort into, but you can get a lot out of it. Resources for furthering your knowledge of R, you can look at the R project page, which is good. The Comprehensive R Archive Network, or the CRAN, which is very reminiscent of Perl's CPAN, is where they store all of the packages. It's the canonical package store. You can also Google search for it. It's gotten better in recent years, but it used to be that searching for a single letter would not necessarily return quality results. So there is RSeek, which is a search engine which is specifically scoped or attempts to specifically scope to articles pertaining to R. And there's so many good books about this that I just picked a couple off of my bookshelf and put them on the slide here. These are all from the Use R ! series, which is generally good. But Peter Dalgaard's Introductory Statistics, The Data Manipulation by Phil Spector, and as far as graphing and plotting goes, I'm a fan of ggplot2. And Hadley Wickham, the author, wrote a very good book about it. So when you are in R, you can also get help. So $command gives you the man page for the command. If you're a Unix aficionado, it's the same as man command. Help is essentially the same thing. If you know the function, but you just want to know the arguments and you don't want to dig through the whole manual page, you can just do args. Question mark does a certain amount of searching. It's not listed on here, but you can also do double question marks and then a term to search for, or you can do help.search. But these are all within the R CLI interface. That's what's being expressed by the angle brackets. So the CLI interface is one of the ways to run R. I'm pretty sure that all of the other ways essentially just mask the fact that they're going back to the CLI interface at some level. So you can get a lot of mileage out of just using the CLI. You can use a GUI, which layers on top of the CLI. Oh, and sorry, for the CLI interface, once you have R installed, you go to the command line, you type R, capital, and you are in the program. Some of the GUIs, like R Commander, RStudio has gotten popular in recent years. On Mac OS, there's a very nice GUI that ships with the default package of R. If you use Emacs, you're in luck because I think that ESS is one of the nicer integrated text editor programming IDEs for R. Look that up if you are an Emacs fan and are looking to get into R. ESS means Emacs speaks S, and S was the predecessor language to R. I'm not sure why that makes sense, but to someone it did. S came before R. The class system in R is like the S3 and the S4 system, but R. And there are many other ways to use R as well. You can use RPy in Python, so you can import RPy after you install it, and then there are ways to call out in a Python script, issue R commands, deal with the results, as well as special data objects that get loaded in that handle like R's vectors, et cetera. Eclipse, if you use a programming IDE, if you're a big Java fan, or sometimes people in general just like to use Eclipse. There's the statet module, which allows you to do R editing and run R inside of it. And there's also, I don't even know if they call it RIPE, but it's RHIPE, which is R on Hadoop. It's like a parallel R framework. So now I'm going to talk about some of the data structures. The first thing to understand in R is everything is an object. And the common types that you will encounter are listed up there, but I'm really going to focus on vectors, strings, and data frames, as well as functions. So I'm going to start with vectors. There are no scalars in R. If you have 3, example, is a vector of length 1. Vectors are, it is a requirement that vectors consist of all elements of the same type. So if you look down here, you can try assigning something like, using the concatenate function, which is C, assigning something to the label of surprise, the vector 1a 2.01, it's actually going to coerce 1 and 2.01 to strings. It will not capture them as numbers. So it's important to understand that vectors will always want every element to be the same type. In this case, it goes from, because it can do a conversion from a number to a string, but there is no numerical representation of A that's unambiguous, they don't go the other way. Another thing about vectors is that you can, an argument like addition, for example, if you have the vector which is 1, 2, 3, so in this case bar is 1, 2, 3, and you add a scalar to it, or what looks like a scalar, because remember it's really just a vector of length 1, it will repeat this vector and apply the same operation on each element of the longer vector. So bar is length 3, 3 is length 1. It will just recycle 3 times. So when you do bar plus 3, each element gets 3 added to it. Seems confusing at first, ends up being like a huge productivity thing once you kind of get into the flow of R. And you're like, all of my values are -1, or 1 lower than they should be. You can either for loop through it and increment each one by 1, or you can do like all your values in the vector storing your values plus 1. So I kind of skipped over assignment, so I'm going to go back up here and talk about assignment. You can use equals. I prefer to use the little arrow that way because it's sort of an unambiguous operator in R. Equals can also be used for default arguments when specifying a function in R. It's purely a stylistic concern, but this is essentially foo equals C is a function, and it stands for concatenate, and concatenate the values 1, 2, and 3 into a vector and assign them to foo. You can get the length of a vector with length. As you can see, it's of length 3. So subscripting is one of the really fun things in R, because there's like tons and tons of different ways to subscript the different data types. So this is all just vector subscripting that I'm going to cover here. So I'm using the sequence operator here. So number colon number means the range 10 to 20. So that's, you can see 10, 11, 12, et cetera. And I'm assigning that to foo. So I've got a vector now, and it has those numerical values as its elements. If I just want to get what's at the first index, I can just throw in an index, and it works like an array in a different programming language. It gives me the first element of the vector. I can slice it. So if you're familiar with Python and you are familiar with slicing a list, you can do start here, go to here. What's really happening is that you're saying the range 3, 4, 5. Just like up here, the range 10 to 20, you're saying give me elements 3, 4, 5. And you can actually do that directly as well. Like I could have put in foo c 3, 4, 5. Put in a vector as an argument for the subscripts that I want to pull back the elements of. You can pass a vector of logicals. So if you pass a vector that is the same length and contains only Boolean values, it will return the elements which have true in that vector. So in this case, I say foo less than 17. And what this does, remember, it repeats the shorter vector argument. So this is turned into a vector of all 17s of the same length as foo. You evaluate this, and this says, where is foo less than 17? And you end up with a logical vector, which is going to be false everywhere that the elements in foo are greater than 17, and false everywhere else. So now you have a logical vector that's the same length as the foo vector. Anywhere where that logical vector has true, you get the results back, which is what you see here. This works with any test that will return a logical vector of the same length. For example, foo modulo 2 equals 0. Is it even? Well, yeah, so it gives all the results that are even. And there's more. So you can name the elements in a vector. If you don't want to use subscripts anymore, you can say, I want to name the elements of foo. Letters just is the letters A through Z lowercased. And I want to take the first 11 because there are 11 things to, or the first 10 because there are 10 things to name in there. And so when you look at it, you've got A through K. And then I can retrieve a value by using that character as the label. I can retrieve a value by using a list of character labels. And then the last thing to know about subscripting with vectors, and this is important if you're familiar with Python, you might like the negative indice number, which counts from the end back. It's not what it does in R. In R, it means exclude that value. So this means do not include the third value, but give me everything else. So you'll notice that 12 is missing, which would be the third value. Another very important thing about R that I usually have in my slide presentations, and I just realized I forgot, is it's one indexed. It is not 0 indexed. The first element is the first element, not the 0th element. So if you want to access the very first thing, 10, it is foo1, not foo0. So if you are coming from another programming language, pretty much any other programming language, this will cause bugs to begin with, and you just need to remember to change your for loops, and I doesn't equal 0 by default in your for loop, I equals 1, and then you change your logical tests appropriately. So vectors is one of the most common data types. Another really common data type is a string. So strings are pretty basic. I didn't put in a whole lot about defining them in general. So double quotes defines a string literal, and you assign it. So the variable my string is equal to the string twinkle twinkle little star, period. String split is a function for splitting strings. And what I'm saying here is it takes 2 arguments. Well, it actually takes a whole bunch more arguments, but it operates with a minimum of 2 arguments, which is what you want to split and what you want to split on. This is actually a regular expression. I was a little bit lazy and just put in a white space character so I could split on white space, but it does accept an arbitrary regular expression. And what string split actually returns is a list of vectors. I didn't go into lists, but a good way to think of lists is that it is a collection of other data types. It's like a Python list, if you're familiar with those. It doesn't care if all of the data types are the same type, like a vector does. A vector is kind of analogous to an array, if you're familiar with an array in other programming languages. So you could have the first element of a list be a string, the second element of a list be a vector, the third element of a list be a data frame or something along those lines. But it returns a list of the number of strings that you're splitting, and that list contains a vector of the splits. So for instance, I am passing, so my string is just a single string. I split it on space, I get a list with one element, and that element is a vector of what, four strings. Aha, that was awesome. A vector of 4 strings. If I assign another variable and I call it my many strings, and in this case it's a vector of 3 strings, and I run the same string split, now I get a list with 3 elements, 1, 2, 3, and you see what's going on there. Continuing on with string manipulation, if you want to append sentences together, you can use the paste function. And in this case, I'm just filling up a dummy variable, for example, complete sentence, repeat buffalo 8 times, capitalize some of them, add a period at the end. So here is the raw, and then you say paste this list of strings, and then when you collapse them with a space in between. And you get, buffalo, 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 buffalo. So for those who aren't like NLP geeks, this is a syntactically or a grammatically correct sentence in English. I'll leave it to you and Wikipedia to verify that statement. Data frames, the last data type that I'm going to talk about. And for most people doing analysis, one that's used, I would hazard to say the most often. It's kind of like a spreadsheet. So you can have multiple columns. Each column has to be the same length, and you can think of each column as a vector. So each column in a table needs to be, have all the same type, and all columns must be of equal length. So for example, I'm going to assign a data frame here, call it my frame, and I have 2 columns. The first one is nums, and it has the values 1 and 2. The second column is lets, and it has the first 2 letters, lowercase letters of the alphabet, A and B. So if I print out my frame, I see, first row, nums column 1, lets column A. Second row, nums column 2, lets column B. Okay, very, very basic as far as that goes. A really handy way to inspect a data frame you don't know a lot about is summary. It will run summary statistics across each column of a data frame. If it's a numerical column, it will usually give you your typical 5 numbers, mean, median, quartiles. If it's a factor, or in this case, a set of characters, it will give you counts of occurrences. So this is a great way to get visibility into something you know nothing about. If you're just handed a data frame and you want to know what's in there, summary is generally a safe place to start. It's almost certainly not going to dump pages and pages of text at you that you can't interpret. Not true if someone gives you something with like 180 columns in the data frame. You'll still get pages and pages of stuff, but at least it's better than trying to look at 180 columns raw. So data frames have their own set of subscripting techniques that you can use. Because they are 2-dimensional, columns and rows, when you're specifying indices for retrieving values, you must put in a comma to denote whether you are talking about the rows or the columns. So in this case, I'm saying my frame, give me the first row. So I get both columns of the first row. In this case, I'm saying my frame, give me everything that is in the first column. So it gives me what would be in the nums column. Now, another way that you can access columns is by using a $ and then putting their label. So remember that my frame has 2 columns that are labeled nums and lets. So if I do my frame $lets, I get the letters that are in that column. Now, did I see a hand back here at some point in time? No? Okay, good. So you can also do logicals. In this case, I'm saying, give me every row where the value of my frame lets equals b. So remember, this is going to reduce to a vector. It's going to reduce to a 2-element vector. And it's going to say true for the second column, or for the second value in that column. So you would basically have a logical vector that's false true. And that would mean false, don't give me the first row. True, do give me the second row, which is what we find here. And you can repeat the same type of operation on the other side of the comma. You can build up really, really insanely complex equations in here to, if it's going to return a vector of the correct length of Booleans, you can probably put it in here and use it as a subscripting index. You don't always want everything that's in a data frame. So the subset function is very important for people that are dealing with, maybe you're getting a massive data set and you only care about 5 columns out of 100. So the data command, as seen here, is something that you can use to load built-in data sets. So R comes with a data set called iris built in. So when I say data iris, I load into the namespace a variable with the name of iris. And it's a data frame that has, I'm only giving the first 3 columns here, but a summary of the first 3 columns. So you get sepal length, sepal width, petal length, et cetera. There's a couple more columns, but they're not really important for this example. So there are 150 rows to begin with. Now, when you're determining the number of rows with a data frame, you don't use length. That gives you something unexpected. What you're asking is how many data points there are, then you want like n row, not length. So there are 150 data points that are in this data frame. And let's say that I only want things where the sepal length is greater than the 3rd quartile sepal length. So they're big sepal length. So I'm subsetting this data frame, which is the first argument. And then when talking about this data frame, all the values in the sepal length column that are greater than 6.4 are going to be assigned to this big sepal length data frame that I'm creating now. And then I run nrow, and as you can see, less values, and the min value 6.5 greater than 6.4. Looks like it worked. And the rest of the output got cut off. But that's the important part. Another trick you can use to make things a little bit less cluttered with $signs and indices and subscripts and things like that is the width function. So like I said, you can get at the values in a column by using a $sign. So iris $sign sepal length is the essentially the column vector of things that are in the sepal length column, and I'm taking the mean of those values. I can also use the width function. So with the data frame iris, so just assume that the namespace I'm talking about is in iris. Give me the mean of what's in sepal length. In this example, this is actually longer, but if you're doing a complex argument, or you are doing, let's say that there's more than a single column that you're passing to the function, you will end up saving space, and it will end up being more readable. So you don't have like iris $sign sepal length, iris $sign sepal width, iris $sign petal length. You can just say, with iris, give me the function, f of whatever, of sepal length, sepal width, et cetera. So these are essentially equivalent statements. OK, so those are I think, probably some of the most important data structures starting out. Has anyone been surprised by anything they've seen so far? Just kind of, no? OK. I'm going to push on to language features if there aren't any questions then. Cool. So let's talk about control structures. We have loops in R. So the R, so this is all typed into the interpreter, but you can also create a text file and then run the interpreter on the text file, and that way save functions and save code, et cetera. But if you want to do a for loop, it's very C-like. So I'm creating a vector here of 5 numbers, 1 through 5. For x in foo, actually that's kind of more Python-like. It's just you don't, you've got parentheses in brackets. So that assigns for each of the values iteratively in foo, it assigns it temporarily the value of x, print x squared. And this is what is being executed for each iteration. And you can see, the squares there. You also have the while loop that you can do. So set a counter, initialize its value. While that counter is less than a certain threshold, take some action using that counter, and then increment the counter as you go along. Eventually, the test will fail, and you'll exit the while loop. Conditionals. Again, if you've done any programming, you're not going to be surprised to see an if-else type of construct here. So, if statement evaluates to true, execute statement. If not, do the alternate statement. And this is just an example where 1 to 5, go through those values. If that value is even, print it's even. If that value is not even, it's odd, so print that it's odd. And there's the resultant output. And then Boolean logic. So in R, all caps true is the true value, and all caps false is the false value. If you change the capitalization, it's not the values true and false. So it does matter that you put all caps. Although one of the nice things about R is you only have to type enough of something to uniquely identify it. I don't know if I have any examples yet, but you can also do capital T and capital F often can be substituted for true and false, which is kind of handy. So when you issue AND to two vectors, assuming they're greater than length 1, the behavior is defined as follows. So you do a pairwise AND. And so you would get what you expect here. False and false, false, false and true, false, true and true, true. And then, again, OR will do the same thing, except with ORs. All right, functions. You declare a function like so, and you can assign it to a label. The arguments are generally positional. So if you have a function with x and y in that order, it will take x and y. The exception would be, if you have defined args or with default args, where you're saying like x equals 1, y equals 2. Now you've assigned a label to them. So you can break the positional structure here, and you can say like y equals 2, x equals 3. So you're actually passing in the value of y first and x second. So not really super innovative, but often very handy.
Question?
Yes?
About the functions. Do your functions have to be in separate scripts?
No.
Everything can be in one,
Yeah.
one long script?
Yeah, so as far as functions go, as long as you have, if you're running a script, I'm pretty sure that you're going to have defined the function before you call it later in the script. It's not going to do like a pre-pass where it goes through and it reads and then figures out all the functions and then executes everything that's not a function. But yes, it can be in the same file. It can be in a different file as long as you're loading that file into the namespace as part of your script. I'm trying to think if I've done an example of that yet. When I get to library in a couple of slides, we'll talk about bringing functions in from other places. So getting data in and out to work on. So let's say I have a CSV file that has 2 columns, and it's just saved on my local file system somewhere as example.csv. And it contains a person, which is a string, and a score, which is a number separated by a comma. And if I were to do a string representation of it, I would see that it's a data frame. And what you can do to actually get at that file is you can use the read.csv function. And then this would be the full path normally. And because I would have a header row, and in this case, let's say that I have a header row which is person score, person comma score. So I'm naming the columns in the CSV file. I can say, header equals true. So here's an example of not needing to type in full arguments. Because there is no other argument that has head, that begins it, I can use just head for the argument header. So the proper name of this argument is header. And again, equals t instead of equals true. So this is using the read CSV function. It will go out, it will read the file from the file system, and then it will interpret it and put it into a data frame that I'm calling x. So when I do a string representation of x, I see that it's a data frame with 2 columns, and then it's a little bit of summary about those 2 columns. Write CSV is very similar. The first argument would be the actual object that you are writing a CSV data frame that you have populated within R at some point in time. And then you pass it a file name that you want to save that file as. Again, I'm using just relative pathing here, dump it in the same directory, but you can use absolute pathing to specify exactly where it goes. And then I'm just passing the value row name is false. So I'm not naming each row of the data frame. Just incremental integers is fine with me. 10 minutes, got it. So there are many other I/O functions along the same lines. So you've got read write TSV, read write delim, where you can specify the delimiter if you want to use something other than comma or tab. Read table, which allows you to do things like specify the data type of the columns that you're reading from a CSV or a TSV file, and also specify the delimiter that you're reading. And then scan, which is really good for bringing in matrices or very large sets of values where it could just be number space, number space, number space with no new lines. And you just want to scan through the file very quickly, and you're going to have R take care of getting the correct dimensionality out of those values. You can also read from the network. So the previous slide I talked about reading from the local file system. So this is an example of pulling from the FluTrends data, the Google FluTrends data. And then I assign basically that handle, something called web data, and I read it with read CSV as if it were a file. And then the skip is just basically, don't start paying attention until 11 lines in. You would look at the text file and then say, okay, there's 11 lines of comments. I don't want you trying to figure out what the rows are until you've gone past 11 lines because the comment lines are really going to confuse it. Newer versions of R, you can also just pass in read CSV and then the URL, which is really neat because that can trim your code size down a lot. And then here's the data that I got. Give me the names, the column names of FluTrends that I retrieved, and it turns out this is one of those data frames that comes with I think 54 different columns. So the first 3 are date, United States, which I think is just the number, and or no, the total for the United States, and then the state with the number for that state. Packages. So we all love code reuse. We don't like to write functions that everyone else has written 100 times. You can benefit from other people's generosity in writing code and essentially install functionality using install.packages. These are generally fetched off the network. So you would hit the CRAN mirror that I talked about earlier. And the example that I have here is the ggplot2 package. So you would say install.packages ggplot2. It would ask you to pick a mirror or a net location to download it from. It downloads the package, it installs it. And then now that it's on your machine, you can access the functions and data in that package by doing library ggplot2. And then I happen to know that ggplot2 has a piece of data or a data frame called movies. So you can load the movies data frame out of there, and I'll be using that in a second. So graphics in R, very simply, you can just do a plot. So this is an XY plot where I have random normal distribution of 100 numbers for the X and Y coordinates, and it's pretty much what you'd expect. And that's just basically plot a vector of values. And so you should have the same number of X values as you have Y values. You can specify things like the main title, the X-axis label, the Y-axis label. Again, the help system and the question mark will get you a lot more things. You can do A/B lines. But as far as just simple plotting, R makes it very easy. If you want to save a plot, you can there are functions like that are called PDF is the name of the function, or PNG, and throw the question mark down and you can get some more data about how to use those. And what these do is these set the default graphical device. They change it from a new window on your computer. So it's not going to spawn a window and show you the plot. It's going to say, oh, OK, when I execute a plotting function, I'm not going to display it to you. I'm going to write it to disk in the format that you have requested. And when you're done writing it, you just turn the device off, and it closes the file handle, and you can access the plot that you have created. Again, I'm going to plug ggplot2 because I'm going to use it in my example in just a second. It's a great plotting library. It has a very good syntax for iteratively building up complex plots. So you can build a layer where you define like a set of axes, coordinates, set the scales, and then put a number of different graphical objects on them. A line graph, and then like a dot plot, and then bar plots overlaid on it. It supports all of that kind of building a plot up iteratively. And that's where you can find out a lot more about it. So I think examples are often very useful in understanding how to use programs like R. So I have a very high impact hypothesis that I want to test here. There is the myth that even numbered Star Trek movies are consistently better than odd numbered ones. So this is important. We want to test this. And I told you about the movies data frame that came with the ggplot2 package. So what that is data scraped from IMDb, which is the ratings of the movies, and it has all of these different columns. I really care about title and rating, essentially. Here's loading the package, getting the data set into the namespace, and then looking at all of the column names of that data frame that I have now loaded. And so there's a column for title, a column for year, and here's the summary of the first and the fifth column, so title and rating. So there's the numerical distribution of scores on IMDb for all of the movies in this data set, and there's the number of times that certain movies appear. So there are 7 movies called The Three Musketeers that have been rated on, or that are in the IMDb ratings. Assumedly, they would have different years assigned to them, which would distinguish them. 5 minutes. So I want to get only the Star Trek movies. So I'm going to use a tool called grep, which I'm going to assume that most people are familiar with. And what that does is that says, look for the string Star Trek in the title, the column movies title. This is going to give me a logical vector. And it's going to be false everywhere where it does not find Star Trek in the title column. And it's going to be true where it does. And then this ig here is ignore NAs. So the R value for null, or not a value, is capital N, capital A. It has consistent but sometimes surprising behavior when it interacts with certain tests like mean, median, et cetera. So there are a number of arguments that you can pass to functions that say what you want to do with values of NA. In this case, I'm saying basically toss them out. I don't want to deal with them. If the title is NA, it's not going to be Star Trek anyway. Yes, in this case it is. Yeah, that's a good point. This could be the ignore case instead of the ignore NA command, in which case that would explain why it's matching Star Trek with capital S's, because you are passing in a regex here. So thank you, good call. So I will get just the movies that match the string Star Trek, and in this case I'm now ordering them. I'm using the with command, so the context is this new data frame Trek movies, which is only going to have movies with Star Trek somewhere in the title, and I'm going to order them by year. So that when I look at then the first, third, and fifth column of the Star Trek movies data frame that I just created, and I look at the first few rows of it, I see Star Trek movies, what I was expecting to see. And here's their theatrical length, and here's their rating. And I don't really care about the Klingon encounter, because this is probably like a IMAX experience at Universal Studios. So I'm deciding that that's not part of the sample that I want to test. So I'm going to say, give me only things where the length is greater than 45. And I'm calling that Trek movies. Okay, so I'm filtering it down a little bit more. So I'm saying, okay, the even ones, right? This is just kind of a gotcha here. If you're used to zero indexing, then you would say, okay, I want the first, third, fifth, seventh, and ninth indices. And when you look, of course, that's the odd number movies, because R is one indexed, not zero indexed. So it bears repeating a lot of times when people are starting with R. I'm using the sequence command here to basically create a sequence that's starts with 2, is bounded on the upper bound is the number of rows in Trek movies, and I'm going by 2s. So essentially, I'm getting the indices that have even number movies, and you can see that here. I'm going to hurry a little bit because I'm 2 minutes, right? So we can see now that the even ones will index the even number movies, 2, 4, 6, 8, 10, assumedly. So let's use a t-test. Okay, so I have was n10 here, so 2 sets of 5, and we get a significant value. So the even-numbered movies are better than the odd-numbered movies. The way that you would run a t-test is you would say t.test, and this is just another function in R, and there's functions for all kinds of different statistical tests. In this case, the arguments are just 2 vectors. And the vectors that I'm passing in are the rating column, the rows that are matched the even ones, and then the rating column of the rows that are not the even ones. So this is the negative subscripting. It works with, you can do a negative subscript of a list of indices and then get everything but those indices back. There's an example of value. Okay, I'm going to blow through this last example. So visualizing data. So this is an example of using ggplot. I actually have a data set that I got from boxofficemojo.com, which is the daily box office gross of movies over like a 5-year period. So, and it consists of like title, the daily gross for that movie, and then the date that the data was obtained on. So let's say that I want to actually load the picture. There we go. So I want to aggregate by day, and I want to figure out the mean daily take on each day for a number of movies. So there's the tapply function, which is basically saying, in the context of this frame, I want you to take the value that's in daily. I want you to split it up so that for each individual date, each unique date, you take the mean of all the values for that date. And this part right here is just a little bit of trickery. I know what it's going to return. I want a data frame that's going to have daily and then date. Those are the only 2 things I care about. You can look at the help page for tapply, and that will tell you how I'm getting these particular, why I have this particular syntax. And here's the plot of that value. So the date, the daily value, I'm saying the data frame that I'm getting it from, and it's the geometry that I'm using in ggplot syntax is I want to make a line graph. So this is noisy. You can also use cut, which says, okay, I don't want to actually look at just plain dates. I want to do it by week. And this gives us a lower resolution, but a little bit more clear view of what average box office take is over, 9 years on a weekly basis. And that and so much more. And I probably don't have any time for questions, so I will turn it over to Bill.
Ask questions while we're moving over.
Okay. Yeah, I'll take questions while we're switching. No questions. Excellent. I have succeeded in my original intent then, huh? Well, thank you all very much.
Okay. And there's our video gone already. Okay. So let's get started, and then we're a very small group here, so if you have any questions, please feel free to ask. And I'll be switching back and forth between some demonstration stuff and some quick code. Like I said, you're not going to learn how to program in Python, but I hope you get a feel for what you can do with it. I'm a faculty at Michigan State University in computer science. I'm also the director of the High Performance Computing Center at Michigan State University, part of the ISO group. And I have written a book on Python programming specifically targeted to CS1 audiences. So there's my shameless plug. This is the practice of computing using Python used as a CS1 book. It's not a reference book, but it's a good introductory book, how to learn Python programming. So what's the first question you have when somebody comes up and says, here's a new programming language and you really should learn this? What's your first question? You know, why? Why should I bother, right? It's an important question and you should ask it because it's all about the time and effort that you have to put into it to learn a new language. You're a scientist, and I assume that that's the people that we're talking to today are graduate students, scientists, budding scientists. You're trying to get your work done. These computer guys, they're crazy for programming languages. I mean, they just love to make this crap up. And why should I listen to you, computer guy, when this comes along? I mean, it takes a lot of time to learn this language, and let's face it, right? I just want to need my work done and then go away, right, if I can. That's the way I'd like to run things. So the real question is, so why? Why would Python be a good thing to learn? Why would that be a good place to start? And that's the one word you want to take away. So the why, the answer to that is it's practical. And we're all about the practical. And so the point being that if you're trying to save time, if you're trying to learn something, if you're trying to do the most for the least, I'd say that Python is a good place to get started. Right? That it's a practical approach to trying to do programming, especially if you're not used to doing a lot of programming. So languages come and go. And again, there are a lot of computer languages out there. It ought to be the case that you reap some benefit. And when we teach our introductory programming language, we teach it to more than 3/4 non-computer science majors. And the reason that the Python stuff has worked for them is because it turns out that they can do work when they get done. And I'll tell you briefly that I taught C++ for 10 years, and never in 10 years of time did a student come back to me having taken one semester in C++ and said, thank God you taught me C++. Oh my God, it made my life so much better. Never happened, not a single time. But I can't tell you how many times I get people voluntarily coming back and saying, I learned Python and I use it in my job. They think I'm a god. They think I can do things that they would never learn to do. And one semester was enough for them to learn that. And so from our point of view, it's a practical experience. So the goal of this talk is not to teach you Python, is to convince you that there's a reason to learn Python and that it's practical for you when you're doing your work. So here's your takeaway. You should see the conclusions in the beginning, right, so you know where it's coming. It's a relatively simple language to learn. And by simple, I mean readable. And I'm going to try to mention this over and over again, that if you can't write code that can be read, then you're not really writing code, right? And there's a good reason for that. There's usually, and this is a phrase in Python, there's usually just one way to do it. Choices are bad, right? You don't want to have choices. I don't want to be told, well, you could do it this way or you could do it that way. There's mostly one, and that's exactly the phrase, there's mostly one way to do it, and that's good. It comes, and this is the other phrase they use, is a batteries included language. So most of the things that you would practically need on a day-to-day basis are automatically included in the language. That it's a practical language in the sense that the things that you normally would come up with are going to be there already. It plays well with others. And so not only is Python a language unto itself, but, and Matthew just mentioned, there's a Python interface to R, there's a Python interface to Fortran, to C++, to C, to Ruby, to PHP, to the web. It's amazing, right? It plays well with others because it was designed to do that, right? And it's a hugely strong open source community, right? That's been going on well for a long time now. And I'm going to switch here real quick. So if you go to the, let me turn this up a little bit so I can see. If you go to the Python package index, you'll see that There are 17,909 currently available packages for Python. 17,909. There's nothing that you want to do that someone else hasn't done something about in Python, right? The first thing you should do is to look in the package index to see what's already there so you can save yourself some time. 17,000. That's a good number. Okay, let's keep going here. I did that already. It also, as it turns out, has a pretty strong scientific presence, high-performance computing presence. I'll show you another list here of a web page that lists the topical software page, which is high-performance computing page stuff that's out there. And the page that I will show you in a second is pretty out of date because it's hard to stay up with this. Because of the fastest growing areas in the Python stuff, the high-performance computing stuff is one of the ones that's growing the most quickly. It's free. It's almost all nice and isn't free good. We would all like to have things to be free, and so here's the topical software page, and these are the areas that they list for high-performance computing, and there's just anything you want in there. And each one of these then is a link to all the packages that would be included if you were trying to do something there. Okay. Supercomputing just ended, 2011. They have their own track for Python high-performance computing. You wanted to see the abstracts, I know. So here were the abstracts that were there at the time. I can't really see that, can you? So working queues with Python, technical anatomy of OpenMPI applications, compilation paths from NumPy to OpenCL, statistical library stuff, integration of a plasma simulator, high-performance astrophysical simulations, parallel computation methods for coastal hydraulic applications. Those were the abstracts for the papers that were just presented at Scientific Computing 2011. And that stuff happens every year. So now your next question is, there must be a catch, right? There must be a problem with this. What's the deal? Why aren't you just using Python? Why don't you know this already? Well, it's not Fortran, right? But a lot of people still use Fortran for really good reasons in high-performance computing. It's interpreted, which you all will probably read as slow. And so one of the things we're going to talk about is, in using Python, how you can still do things quickly, but do them in a way that's more manageable than you would otherwise, right? And you don't know it yet. So what's the goal? The goal when you're writing code like this, especially if you're a graduate student, is it should be simple first, then fast. Fast should never be a goal, right? Because fast is always bad for writing code, right? You want to write code simply, which is almost always going to be slow, and then you want to fix it to be fast so that you know what it does. So the mantra should be develop code simply as possible, and the best way to go is speed is not a goal, but quality is a goal, right? You should write stuff so that it can be read, right? You only have to make the slow parts fast. Duh. Right? So if you can figure out what the slow parts are, then you can worry about those things and do only those things that are required. Readability is important. You are going to have to read this crap somewhere down the line, right? And you are the one that's going to suffer if you can't read it well enough to fix it when it needs to be done. And Python allows you to do that more readily, right? So the mantra is this: do as much the easy way as possible. Right? And then find the things that are hard and work hard on those. Right? That should be the way you build code. Right? And and we can all shake our heads and go, yeah, that's a really great idea, but people don't do this. Right? They sit down in their C++ compiler and they say, well, I don't want to do that array index. That'll make things way slower, so I'm going to do this and I'm going to do that. And, right? It's not the way to do it. Write it so that you can read it and then fix the slow parts when it comes up. So Python for science. Python allows you to do all the grunt work that you normally need to do. Read files, build GUIs, do the graphing, do the plotting, do the data manipulation, get everything ready for the hard part that's to come. And then with the stuff that's left, if you need it to go faster, you can reach out and use either packages or other programming languages so you can get the work done. The idea is that you want to focus your efforts. Work hard where you need to work hard and work easy where you can just get the work done. Right? And this should be the way you write code. So what I'm going to do now is I'm going to do a blitzkrieg move through Python, starting with just what the basic layout looks like, and then I'm going to move all the way through a bunch of high-performance computing type applications. Sadly, and I only sort of got a feel for this when I was sitting in the previous talk, I don't have a lot of biology examples, and I sat down and thought about that. There's lots of biology applications for Python, but they're not high-performance applications, and so that's one of the places where things seems to be lagging in Python at this point. There's a whole BioPython package for alignment and clustering and sequencing, interacting with databases, but not a lot of high-performance stuff yet, which could happen, but isn't out there yet. So let's look at some code. Let's see if I can do this without it falling off. And so this is what I want to do for the rest of the time, is sort of go back and forth. So this is, that's not it, but this is a COLAT sequence. Anybody know what the COLAT sequence is? Okay, well, I have a web page for you. Oops. I don't know what that is. One more. So the COLAT sequence is one of those little math things that everybody knows is true, but nobody can prove. And there are a lot of those little guys out there. And here's a real simple view of the COLAT sequence. Take any integer. If the integer is even, divide it by 2. If it's odd, multiply it by 3 and add 1. And the conjecture is that from whatever integer you start at, it'll always end in 1. And they use it as a way to burn in CPUs, right? Because every integer they've ever tested, up to the trillions and trillions, always does this, but they can't prove it mathematically. So here is the COLAT sequence in Python. And I'm not going to go through it in detail because you'll be bored, but I just want to show you it's got all the regular features, right? It's got assignment statements just like you normally would have. It has math. It has if statements, elif instead of else or if, an else statement, plus equals for addition, division, multiplication, all the kinds of things you would normally expect. It's all in there. Here's the guts of it. For some particular number, if it's evenly divisible by 2, we divide it by 2. Otherwise, we add 3 to it and 1, and then the rest of it's just to print it out. Nothing spectacular there. Looks pretty simple. A couple things that we should note about it that are interesting to know, and I'll come back to it in a second. Variables are untyped in Python. That's both good and bad. It's good for doing quick coding and getting things working to try to see how it works. It's bad for speed, right? But we don't care about speed, do we? Right? We're going to worry about speed later when we get stuff working. It's an association between a name and an object, so almost everything's a reference in one way or another. Comments start with a hash sign. Print formatting is similar to the C's print formatting: while, if, else, f, plus equals, minus equals, but no plus plus or minus minus. All the I/O is by strings, from files, from web connections, from anything else. Pretty normal stuff. More interestingly, blocking is not done with braces. It is done with indentation. And if I go back and look at the code, which I will in a second, you associate a group of code by indenting it appropriately under a header. Right? And I'll say this now, it totally weirds people out. When I tell them that, it's like, what? There's no braces? How the hell am I going to read it? And it cracks me up because, in fact, if you go back here, it makes it ever so much easier to read this stuff, right? If I could just get the scrolling to work. So where does the while begin and end? You can see because those things that are indented belong under the while statement. What about the stuff that's indented under the if? That's the part that belongs to the if. It's an invisible marking, but it's done, why? To make it more readable, to force you to write better code. No matter what I tell you, no matter what I give you, you can all write horrible code in Python. It just makes it a little harder to do by putting these kinds of things into it. So blocking is done in that way. There's an odd else construct, which you might see, which goes with almost every control construct, not just with if and else, but also with while statements, for statements, everything else. An else statement associated with a while group is the exit condition. So if you want to say, look, the while loop just ran through and the condition ended and I'm done with the while loop, and you want to do something on the way out, that's the else clause. If the for loop ends, you get all the way through and you want to do something on the end out, that's the else clause. You go through some process and you want to do something on the way out, it's the else clause. So it's an exit kind of thing. Odd phrasing, I assume, but that's the way it works. Palindromes. Madam, I'm Adam, right? But when you do palindromes, there's some things you don't do. You don't pay attention to capitalization, you don't pay attention to spacing, you don't pay attention to punctuation. So when you're doing palindromes, you want to strip those things out so that you can do comparison of the sequences to say whether the order of the letters is the same forward and backwards, right? So here is a bunch of different ways to do palindromes, and this is my way of showing you functions. Here's the stupid, slow way that you probably learned when you were learning C. You start at the beginning and the end, right? And as long as the thing you're looking at is not one of the things you care about, which is the lowercase ASCII letters, you're going to walk in until you get to a letter. From the end, you do the same thing. If it's not a space, if it's not a punctuation mark, that's what you don't care about. You keep walking until you get a letter. Once you hit the two letters, you compare them. If they're the same, do the same thing. You walk in from both ends till you hit the middle, right? If you make it to the middle, then it must have been in palindrome. As soon as you find something that doesn't match up, you're out. That's what that one does. Let's see, here's some better ones. These are all little functions. Here's a way to just do it by reversing a string. This is more Pythonic, and that you'll hear that word. Take the string in, lowercase it, go through every bad character in a known list of bad characters, and if it shows up in your string, replace it with a blank. At the end, and this is a shortcut for string reversal, take the string, reverse the string. If they're the same, you're done. If not, go away. So here's a recursive version, so on and so forth, all kinds of different ways. That's a recursive call to do it, which is really slow. To test it, here's a make palindrome, to make really, really, really big palindromes, like thousands and thousands of characters long, so we can test these things. And these are all timed so that we can see how long they take. Interestingly, the way you do the timing is that you write a timing function. So here's a timing function. It takes as an argument, interestingly, another function. It's called a decorator, and what will happen is whatever function I take in, it brackets it with time and prints stuff out about it. When I want to time a function, all I need to do is, oops, wrong one, put this guy in front of it. So the name of this wrapper is called print timing. I'm going to put the @ sign in print timing, and now this is the function that's going to get wrapped. So if I want to time this function, I put the decorator on top of it. I'm done timing. I take it off. I don't mess with my code in order to get it to work, right? So you can wrap these things as much as you want, keep the core code working, unwrap it by taking the decorator off and make it go away. Very, very slick way to try to do some experiments. Python is all about experimenting with this stuff in the interpreter so you can see how it works before you go on to the big stuff. Let's see, what did I miss when I talked about this then? Oh, the for loop is not a for loop like C. It's more a for loop like Matthew was talking about. It's an iteration through a sequence. But what's really nice about Python is the for loop works with everything, right? You can iterate through a file. You can iterate through a web page. You can iterate through an internet connection, through a data structure, through anything that's set up, because the expectation is that if it's a chunky thing that's got parts, you can iterate through it with a for loop. So it's about iteration through things so that you can look at them. And what did I iterate through here that would have been interesting? Oh, so here are some bad characters. So the characters in string.whitespace and string.punctuation are the things I want to ignore. So I'm going to go through all the bad characters and these two things taken together and replace them whenever they come up. Very nice stuff. And you can expect that that would work then pretty much with all the other stuff you're working with. String is one of the data structures. There's others, dictionaries, hashes. They can be indexed, they can be sliced, which you just saw. Depending on the type of the method, they have different, the type of the structure, you have different methods associated with it. Some are mutable and some are immutable, which is interesting because everything is a reference in Python. When it gets passed, it can be modified, but some of the data structures are marked as unmodifiable. So instead of saying that it's passed by reference or not by reference, if you pass the correct data structure, you can or don't change it. Functions are made with a def keyword, take lists of parameters, everything's a reference, can return a single value, all pretty expected. I just told you about decorators. You can do functional mapping. It has some things in it to do, so you can say, look, I want to take a function, I want to map that function across this whole sequence and iterate through all those things, so I can take an array, map the whole thing to be multiplied by 2 and return it. That's a faster way to do iteration kinds of things. Very nice. Here's a word frequency, and these are all things we do in the introductory CS class. And so these are all examples that they would see or be able to write against. So here's a word frequency. I asked them to do the frequency of words in the Gettysburg Address. And this is the guts of it right here. So a file object is an open file for a line in the file. When you iterate through a file, you get a line. When you get the line, you can run a split function on it, and the split function takes the text line and splits it according to some character into a list of smaller strings. If you don't say what the split is, then it's by white space. So if I take a text line in and I say split it, it's going to give me all the words, space identified elements in there. I now have a list of words, and then for each word in the list, I lowercase it, strip the punctuation out, all this crap just to get a single word. Right? And then I ask a question. If the words in a dictionary is a hash table of pairs, right? Key and value. So everything that runs in this thing is by key. Is a key in there, then the value goes up by 1. If it's not in there, I put it in the dictionary. Bam, I'm doing word stuff. The rest of this stuff is just to print it out in cooler or more interesting ways. Print by frequency, print by orientation, and this is all exercises that they would have to be able to do. I'm not going to run those because I think they're pretty obvious. That's what I just said. Rational number class. Here's an object that you can make. It's all object-oriented. There is a lovely fraction class in Python, but I won't let my students use them. I make them write their own. Here is the class, pretty easy to understand. Keyword class, rational, inheriting from object. These are methods. They're indented underneath just like all other things are. And see, these are the methods now in my class. Some of them have special meanings. I don't like this, but this is the way Python does it. It ends and begins with double underlines. They have special significance for Python and when they get called. This is the initializer. This is a conversion to a string that will print it out. This is the addition, so I can do binary addition on the object. This is equal, so I can do equivalence on it. And so that the program will do all these things, right? So I can make a new rational number, I can compare them, I can add them, do all those things. Pretty easy to do. Right? Again, if you've done object-oriented programming, this looks pretty normal to you, right? Does that make sense? So this is all I'm going to teach about Python. Anything else you want to know? Yeah? It does. Okay, let me just say this, because I love this. If you ask me a question of one or two types, is it in Python or is there a way to do it in Python? The answer is yes. Absolutely. The question is the gain for pain ratio. That's what you want to know, right? How hard is it to do in Python? There is a regular expression system built into Python. It's called the RE system, and it does pretty much like Perl does its regular expression stuff, all there. Any other stuff? Because I'm going to move on to HPC stuff. This gives you a flavor, at least, for how Python works. Yeah? Yep, it has a built-in OS module, allows you to get to the operating system, do all the regular stuff that you would want to do, network calls, all that kind of thing. Yep. Other stuff? Yeah. Anybody? Nope. Let's keep going. Oh, I should, a couple of things, I guess, about the object stuff. So, pretty obvious how it works. It's like Smalltalk and not C++, if you've never done Smalltalk. In C and in Java, the implicit nature of the call on an object is that the object is bound automatically, usually to a variable called this, which, by the way, when you're teaching a class to introductory computer scientists, the this variable is a real pain in the ass because it really screws you up when you try to talk about it. In Python, like in Smalltalk, they assume that the first argument in every method call is in fact the object. And so it's automatically bound, and you're no Python programmer if you don't call that first argument self. So the object is automatically bound to the method, and then manipulation of the calling object is through self automatically in all those methods. And I'll go back and show you that again. The overloaded operators. Python is not big on privacy. They don't really care. Right? And this is their phrase. We're all adults here. You can mark something as, I don't think you should mess with it. I think it should be private. But hey, do what you want. Right? If you want to go and mess with the private variables in my class, go for it. I don't care. But it's your life. We're all adults here. You know what you're getting into. That's the way it works. So there's no public and private. There's no maintenance of that kind of stuff. You can mark them and say, I want them to be private. It's obvious to anybody that gets in there. Screw with it at your own risk. That's the way it goes. Tools. There are actually multiple interpreters depending on what your goals are. CPython rather, is the C interpreter that you would get normally. Jython, and you'll get really sick of this pi this and thon that, but that's the way it is. Jython is the Java JVM interpreter. The advantage being that you can run in the JVM and you get access to all the Java APIs. IronPython, which is a really great name, you gotta like that. Microsoft uses its own interpreter, and it gives you full access to the Windows API. And there's other ones like PyPy, which is a just-in-time compiler, uses the JIT, stuff like this. This is the basic list of the scientific tools that you would get if you were trying to go out and reach for it. IPython, which is the interpreter that I'll show you in a minute, is the interface, the console that you really want to work with. It's very, very nice, gives you access to the underlying operating system, plus lets you do Python stuff at the same time. NumPy, usually people say NumPy, but I just can't do it because it's too easy. NumPy is the way to carve out C-type arrays, solid pieces of memory of a particular type, so that they can be passed back and forth, as well as manipulations of matrices and vectors. SciPy is a huge toolkit for doing scientific manipulation, and Matplotlib is a straight-up copy of the MATLAB plotting stuff. Gives exactly the same plots. You can do quality plots with this. So this is the, you really can't see that, can you? That's too bad. These are all the tools that come with SciPy for manipulation, automatically out of the box. Clustering, distance computation, sparse matrices, multidimensional imaging, optimization, orthogonal distances, all that stuff's built in. And each one of these are underlying C libraries, so they're an optimal C libraries, so they go fast. So you set up your data, you stuff them in there, you make the calls, it does it as fast as it probably will do it anywhere else, and you bring them back and use them. So as an example, let's look at a fast Fourier transform. And let's see, how do I want to do this? I'll just call it first, and then I'll show you what it looks like. So this is a call out for the fast Fourier transform, and it generates a plot for me automatically. And there's the two nodes of the fast Fourier as it came up. And if we look at this code, it's pretty easy to set up. What it did was, boy, it just don't want to let me do it. We set up an array. This is a NumPy array from 0 to 0.61 by 1 over the sample rate as increments. That's how long it is. Let's make a sine wave out of it. So we apply that to this big array, push it through all of those guys, and so the entire array of however many elements there are in there are signed in this way. Let's run the FFT on it, see what the rate looks like, and see what it comes out. And then, oh, this is the plot, right? Plot this thing and show it to me. I didn't need the show. I just put it in there. Right, so the plotting library is pretty easy to go, and there are a lot of these kinds of libraries, and they go very, very quickly. They run very fast, and they're very efficient. There'll be a lot more of this kind of stuff. HPC stuff, there's a lot of things underlying it to go fast. There's a threading model, there's a multiprocessing model, there's an MPI model, there's a PyCUDA model for CUDA processing. Here's a simple one. How do you calculate pi? An easy way to do it is this. You draw a circle, you draw a square that sits on the center point out to the radius, and you throw random spots down into the square, I'm sorry. And you count the number of points that show up inside the radius of the circle, and the ratio of the total number versus the part in the arc is pi over 4. The more dots you use, the more accurate it gets. We can do this in MPI. For those that don't know, that's the message passing interface, right, which is a way to set up multiple calls on multiple computers to run a piece of code. This is the MPI code, and if you've never written MPI code, you wouldn't know, but this looks exactly like the kind of MPI code you would write in C, except it's in Python. And when it gets run, and I'm going to have to copy this because I set all this stuff up on my local machine because I was a little afraid of the network here. You would call it pretty much in exactly the same way. So it says I have 4 processors on the machine. It's really only 2 because of hyperthreading, but you get the idea. So you'd call it the same way. That would start 4 independent processes up, communicating with the MPI. There are the 4 processes reporting back out, and it's 3.1419, not bad, right? For I think it's 1,000 points or something like that got thrown down. More points, more processes would run better. So you can write message passing interface code, you can write parallel code just like you would have been taught in C, only it's a lot easier because all the initialization stuff gets done for you. That's another one. How much time do I have? How am I doing, Matt? Do you know? 47. Thanks. Here's PyCUDA. So I'll show you the code, but you're not going to know anything for having done that. What I want to show you is the first line, really. So CUDA, if you don't know, is a common Common Unified Device Architecture. It's the interface that NVIDIA has designed so you can use their GPUs to do computation. It's horrible. Anybody done CUDA programming? Do you like it? It's tough, right? It's tough to get the hang of what you have to do because it's very, very specific. Here's what's cool about CUDA for Python. This line right here, that sets it up. Call the auto init. It gives you a pipe and all the stuff that needs to be done in order to make communication go back and forth. And then it's a matter of moving things back and forth between the device, making the call and running it. You can only code in C through NVIDIA's architecture, and so you can write your code in C as a string, send it down, run it, drop it back out, make it go. Right? So it doesn't make CUDA coding easy, but it makes it easier because it takes care of all the crap work that you have to do in order to set it up and tries to get you to focus on those things that actually make it run. And what does this do? Oh, this takes a big array in and doubles it. It does it a couple of ways. Here's a more interesting one. Yeah, go ahead.
How does the C code get compiled? The GPU code?
PyCUDA does it for us on the way out. So it calls the NVCC compiler as it makes it go and stuffs it into the GPUs to make it run. So it takes out all that out of your hands. Here's the Mandelbrot set. I needed to call it with, and this gives me different ways to call it, but let's just do it GPU straight. This is 300 iterations over the whole Mandelbrot set, and there's the graph, and it took just that long to run. Right? If I was to run it under regular Python, we'd be here for a while. Right? Straight up calls to the CUDA architecture. What's next? Interoperability tools, this is what you want to know about. There are a lot of them, as it turns out. Boost Python is a full interface to C using the entire Boost library as well as the STL. Fortran stuff. Swig is an interface for any interpreted language, but it works. Pyrex is an inline declared C-like kind of context. So you take your Python code, but you stick C-like things into it, right, which will do what they're supposed to do. They get called the way they're supposed to get called. Psycho, which is my favorite term, and I still can't get it to run as a fast Python compiler. SciPy brings two things, Weave and Blitz. Weave allows you to inline C code in your Python so that if you want something to run in C, it will do that. Combine them together, build it as a library, make it go. And Blitz will just take your NumPy code and translate it into C before it actually does the run. Just to demonstrate, I'm not going to run this, but I want to show it to you. So here's an example. So here's a C++ array class with a node and a mesh and all the stuff that you would normally do with C to make one of these guys. There's some stuff at the bottom that exposes this as a library. And then having used the Boost library, I just call it. I import it. That's an array classes node, makes a node, makes a nodes, makes a mesh, appends it, does all the things I would normally do for Python. So it gets me the access to that C++ code pretty easily, right, just by introducing it that way. So all the things I did with that C++ class are now available in Python, so I can make it run. Let me just show you the next one. This is, I'll show you the whole demo because it's kind of cool. But this is a call out to a piece of Fortran code. That's the Fortran code. I imported it, made the call. This is a Laplace solution for a very simple two-dimensional box kind of layout. This is a call to the Fortran code. It got set up, and I just imported it as a library. It gets run as Fortran. There's the straight-up Fortran 77 code that it would have called to make it go. So you can take existing Fortran code, compile it with F2Py, Fortran 90, Fortran 95, Fortran 77, doesn't matter which one, store it up as a library, get the optimization you want, and then just import it where you need to. Do the easy stuff in Python. Use your existing libraries to do the hard stuff as you wanted it to go. Let's do a quick call here on that. So what's interesting about this, let's see if I can do this, is this gives me all the different ways to have run it. So this is, it's going to run the same Laplace in like 5 different ways and sort of give you the timing. So this is using straight up numeric Python. This is a 1,000 by 1,000 grid, 3.8 seconds. Blitz is one of the SciPy ways, inline C. Here's a better inline. Here's an even better inline, different ways to do it. This is Pyrex, which is the inline again. This is Fortran 77 for the time step. Fortran 90 arrays for the time step. Fortran 95 for the time step. This is what you would do if you did it in Python. It would only do one iteration out of the 100 because it's too painful. So it would have taken 724 seconds to do that in Python, just using it in a stupid, dumb way. But with all these integrations, you got it down to as many as 1.5 seconds to make it go. So that's the boost demo. So here's the end. Right, it's an easy way to get stuff up and running. If you don't know how to do MPI, you can experiment interoperably with MPI here in the interpreter to see how it goes before you write the code. That's great. Same with PyCUDA. You can type things in and see what happens. It has all the tools that you need to make your tasks easier for a lot of things like graphing and GUIs. It can be integrated with other stuff. So if you have Fortran code or C++ code that does something hard, but you want to put a GUI on the front of it, you want to graph the results, you want to store the files, you want to bring files in from other places, Python's the way to do all that stuff, and then you just call your code directly. So the bottom line is it's a great foundation for scientific programming, and that's what I'm trying to tell you. And I hope that's what you took away from it. And that's all I have. Thanks very much. And if you have any questions, I'd be happy to answer them. No? That was so obvious. Okay, thank you.